Hello and welcome to this third video on Chapter 5, Geometric Applications of Differentiation. Okay, what are we going to be looking at today? We're going to go through and describe what concavity is and what it means for different functions. We're going to identify what a point of inflection is and what a horizontal point of inflection is, and then we're going to go through a summary of critical points in general. Okay, first of all, what is concavity? Well, concavity is what I like to say is the shape of the curve. So not talking about the gradient itself, but talking about how the shape looks. And what I mean by that is kind of saying if it looks more like a bowl or a hat. And it's a weird analogy to use, but it's probably the best thing to think about, right? So if we have a look at this function here, if we were to continue this part going along here, it looks like it would go up, right? It would continue to go up and would just stop there, right? And then this one here continue to go down. And at no point would they actually turn around and for some reason go the other way. They're going this way, they're going to continue going this way. And that's essentially the best way to tell what the concavity of a curve is. You can visually and intuitively see which way it is. This one is a smiley face, right? This part is forming a smiley face, and this part is forming a frowny face, right? Remember, frowny face is sad, so it's a negative concavity. This one is a positive concavity. So we didn't actually mention in the last video about the fact that this was concavity, but when we're talking about the second derivative, when we were testing the maximum or minimum turning point, we were actually testing the concavity at that point, and that was directly telling us whether there was a maximum or minimum turning point. In this case, we know that this is going to be positive because it has that smiley face there. Now, some of you may ask the question, what happens in between, right? Because whenever we've got something happening where we go from a negative to a positive, and it's a continuum, it's a continuous function, at some point we need to cross over zero, right? We need to cross over zero at some point. Well, very good question. And the answer to that is a point of inflection. All right, we'll get to what this important note is at the end. When we're talking about a point of inflection is that point in between those two concavities, the positive and negative concavity, which has a second derivative of zero. So it doesn't have any concavity to it. And we're going to show how you can find these points of inflection using the second derivative. So for finding points of inflection, you need to use the second derivative. So the function that we're going to be using here today is we're going to use y is equal to x to the 3 minus 2x squared minus 3x plus 4. Okay, let's derive this once. Y dash is equal to 3x squared minus 4x minus 3. And let's derive it again. Y double dash is equal to 6x minus 4. Okay, always good to go through when you're actually going through a question is to think about what you're doing at each step. Okay, so what would this step actually tell us? If we wanted to use this, we could actually find out using the quadratic formula here what our two different turning points were, right? We're going to have two different turning points because it's a quadratic formula. And at this step here, we're going to be able to tell what our points of inflection are. And we could also use this second derivative to figure out what the nature of those turning points from up here were. So just when you're going through questions, always ask yourself, what could I do at this step, even if you don't actually need to do it for that question. Alrighty, so for this one, we've got 6x minus 4. And to find a point of inflection, you just let the second derivative equal 0. And then you solve. So 6x is equal to 4, x is equal to 2 on 3 when we divide by 6 on both sides. So x is equal to 2 on 3. And what that means graphically, if we want to have a look at it, this will not be an accurate curve because we haven't actually found the turning points. We could go around and find the turning points and that would give us an indication of where the curve sits, but we haven't. So what we're actually going to do is just approximate that this is what the curve may look like. But the thing that we do know is that it's going to have a turning point at the x value 2 on 3, right? And that point of inflection once again means that it has no concavity and it's going to be in between this positive concavity and this negative concavity. I do, however, know the approximate shape of it as well, because remember from the last couple videos when we were talking about the direction of arrows, these are going to be pointing in opposite direction because it's an odd power, and since it's positive, this one's going to be going up this way. Radio. So that's what a point of inflection looks like. And when we're talking about our second derivative and looking at concavity with that, we don't necessarily care that much about the actual value of our curve, right? So when we're talking about up here, and it's relative to down here as well, is we don't really care for our second derivative what the actual number is when we put in, say, this value here. We don't care at all what the value of that number is. It's all about whether it's positive or negative. Because only in extension 1 or 2, when you're dealing with acceleration, are you going to actually worry about, okay, what is the acceleration at this point? We don't actually need to worry about that. All we need to worry about is whether at this point it is positive or negative. Alrighty, and I said I would come back to this important note here, and this is actually something that people miss a lot of the time when they're going through and talking about points of inflection. A second derivative of 0 does not necessarily mean there is a point of inflection. But hold on, I just said that to find a point of inflection, we let the second derivative equal 0. Well, yes, that is true. All points of inflection will have a second derivative equal to 0, but not all times a second derivative is equal to 0 will there be a point of inflection. See, it's one of those weird syllogisms, and there's a reason for that. Let's have a look at the function y is equal to x to the 4, right? What is the derivative of this? Y dash is equal to 4x to the 3, and the second derivative, y double dash, is equal to 12x squared. If we want to find out where the point of inflection is, right, we let the second derivative equal to 0, right? So second derivative equal to 0, and we would get x is equal to 0. Pretty easy. But the thing is, when we have a look at our function of y equals x to the 4, right, y equals x to the 4 is actually just a slightly shallower version of y equals x squared to start with, and then it accelerates further. There is no change in concavity, right? From this point here to this point here, across the point x equals 0, there is never a change in concavity. And for there to be a point of inflection, you need a change in concavity. It's not enough for the second derivative to equal to 0. You need a change in concavity to occur to actually make sure that that is a point of inflection, right? And we can actually, the way that we test whether something is a point of inflection or not is we can actually use a table of values for the second derivative. So what I'm going to do here is I've got my x values and I've got my y double dash values. So I've got 0, minus 1, and 1. If we put minus 1 into the second derivative, we're going to get 12 because minus 1 squared is 1 times by 12 is 1. At 0, we're going to get 0, and at 1, we're also going to get 12. So we have positive, 0, and then positive. And that's not a change in concavity. That's the same concavity. And the thing that's actually causing this weird funky thing to happen here is we actually have a double point of inflection on the same point. You don't need to worry about that. That's not something that's tested. It just may be good to know that that's the reason that it's occurring. Okay, let's have a look at some past paper questions. So the cubic y equals ax to the 3 plus bx squared plus cx plus d has a point of inflection at x equals p. Show that p is equal to that value. Okay, what does a point of inflection mean? A point of inflection means at that coordinate, the second derivative must equal 0, right? So y dash is equal to 3ax squared, right? So taking the power down the front, taking 1 off the power, plus 2bx plus c, that's the first derivative. Our second derivative, y double dash, is 6ax, bringing the power down the front, taking 1 off the power, plus 2b. X is normally to the 1, and then we take 1 off that power, it's going to be x to the 0, which is just 1. And we know at the point f double dash, so subbing in x equals p, we will get a second derivative of 0. So what we actually do, we put p into our points of x, so we get 6ap plus 2b is equal to 0. 6ap is equal to minus 2b. P is equal to minus 2b on 6a, or equal to minus b on 3a when we simplify. Right, and that's the solution that we needed to get there. Okay, the final thing that we've got to look at is horizontal points of inflection. And these are another funky thing that occur with functions. And the easiest time to look at them is in the function y is equal to x to the 3. What does this function look like? Okay, it looks like this. Roughly like that, not perfectly. Okay, let's have a go deriving this and just see what happens. When we derive once, we get y is equal to 3x squared. And when we derive twice, we're going to get y double dash is equal to 6x. Okay, so if we wanted to find a point of inflection, right, what we would do is let this equal 0, and we get the point x is equal to 0. Okay, so that's saying that at the point x is equal to 0, we would have a point of inflection. If we sub 0 back in, we get 0. So the coordinate of a point of inflection should be at 0, 0, point of inflection. But now let's have a look at to find a turning point, right? So looking at our turning point, we've got y dash is equal to 0. So we get 3x squared is equal to 0. Wait, x is equal to 0. So at the point 0, 0, we have a point of inflection, and we also have a turning point. And that's what the horizontal point of inflection is. We can actually see visually that we do go from a concave down to a concave up, right? We can visually see that we do have a change in concavity, and I'm actually going to show this using a table of values. So let's put our x here and our f double dash x down here, and we're going to do -1, 0, and 1, and our second derivative is there, so we're going to be using that. So we'll get -6 here, 0 here, and +6 here. So we actually do get a change in concavity. We go -0, positive, right? So we do get a change. There is a turning point, a point of inflection there. So that confirms a point of inflection. But we've also got a first derivative equal to 0, which means there also must be a turning point. And that's fine, right? Well, I say fine is in the fact that there is a first derivative equal to 0, but not necessarily a turning point there, right? What I mean by this is that it does go horizontal, right? If we take a close-up look at what's actually happening at the origin, it does this. It does go to horizontal completely at that center point, but there is no turning point there, right? So it's not a turning point as such. When we've got a turning point and a point of inflection together, we combine them into a point of inflection. Because if we were to test the first derivative, right, use a table of values, so horizontal point of inflection. If we were to test the first derivative for a turning point, which I'm going to do now, so we've got x and f dash x. So we're going to do -1, 0, and 1. If we put in -1 into our first derivative there, we're going to get 3 times by -1 squared, which is going to be 3. Put 0 and we're going to get 0, and 1 squared times by 3 is also 3. So we get no change. No change, right? So to prove that a point of inflection exists, you do not have to test this. All you need to, horizontal point of inflection. To show that a horizontal point of inflection exists, all you need to do is figure out that you have a first derivative equal to 0. So first dash equals 0. So y dash equals 0, y double dash is equal to 0, and then use a table of values for the first derivative for y dash, right? So that's all you need to do to actually prove that a point of inflection does exist at that point is y dash is equal to 0. Okay, there's a horizontal point there. There's a stationary point. Y double dash is equal to 0, so there must be a point of inflection there. And then testing a table of values for y dash will also give you the fact that there is no turning point, so it must be a horizontal point of inflection. Okay, just to consolidate all this stuff that we've spoken about, because even I sometimes get muddled up on the words on the actual definitions between them, I've just created a little table down here as a summary of our critical points. Right, so let's just go through this quickly. So y dash is equal to f of x is our first expression. It is our function value, also known as our curve. And what does it show? It shows the relationship between a set of points on the number plane, right? It's just saying, okay, if we have a rule that connects these 2 points, this is the curve that all the points obey that rule by, right? And what can it be used to find? It's used to find a pair of corresponding x and y values on the curve. That's all we really use the function value for. And that's all it needs to do, right? The y equals f of x value, that's all it needs to actually do. When we have y equals f dash x, this is known as the first derivative, as we've spoken about, and it gives us the gradient of each x coordinate on the curve. So the corresponding x coordinate on the curve will have the gradient of this. And we can use it to find gradient and stationary points, right? So important here is something that they may have tripped up while I've been talking about before, is I've been saying turning points. And that isn't necessarily correct. The correct term to use is a stationary point, because a stationary point can be a horizontal point of inflection or a turning point. All that it means is that the curve goes horizontal at that point. So it's good to say when we're talking about the first derivative, it only really finds stationary points. We would then need to use a table of values to confirm if that is a horizontal point of inflection or if it's just a normal turning point. And finally, the second derivative, also known as y's f double dash x, is the rate of change of the gradient. This is technically what it's actually saying. It's saying how fast is the gradient changing. I don't really like to introduce this to students unless it's necessary, because this concept is really hard to wrap your head around. It's saying how fast is the rate of change changing, which isn't really that useful. What you just need to remember is that it can help you find a point of inflection, so that, or when the second derivative is equal to 0, it will not necessarily be a point of inflection, and it can help establish the nature of a turning point. Alrighty, so we've went through a lot this lesson. So we've described what concavity is, we've identified points of inflection and horizontal points of inflection, and summarized critical points.